So in today's video, we'll be covering the topic of binomial theorem. Now, before we delve into binomial theorem, we must need to understand what a binomial expression is. So any expression consisting of two terms is called binomial expression. So let's say we have an expression a plus x. Since this expression has two terms a and x, this expression is called a binomial expression. Now, the binomial theorem is used to determine the expansion of such binomial expression raised to some positive exponential value, since such expansions cannot be simply derived through mere repetitive calculations. Had this been raised to the power 2 or 3, I would have used the formula of a plus b whole square or a plus b whole cube. But if it's a plus x whole to the power, let's say n equal to 7, it's very difficult to expand it by using multiplication, mere repetitive multiplication. So that is where we use binomial theorem. Now, the formal definition of binomial theorem is the algebraic formula by which a binomial expression raised to a certain positive integral power can be expressed in the form of a finite series is called the binomial theorem. And the finite series is called the expansion of the power of the binomial. This binomial theorem was discovered by Sir Isaac Newton. And I have the statement of binomial theorem written here as follows. So if we have the expression, the binomial expression a plus x whole to the power n, that can be expanded in the form a to the power n plus nc1 a to the power n minus 1 into x, plus the second term will be nc2 a to the power n minus 2x squared. The third term will be nc3 a to the power n minus 3x cubed, so on until the r plus 1th term. Please remember that this is not the rth term but the r plus 1th term. Why, you ask? Because this term is the second term, but we have 1 over here. So if we have r over here, this will be the r plus 1th term. So the r plus 1th term is ncr a to the power n minus r x to the power r. Moving on, we have the second last term nc n minus 1 a into x to the power n minus 1 plus the last term being x to the power n. Of course, this binomial theorem can be proved by principle of mathematical induction. I will be doing a revision exercise on the principle of mathematical induction that I had discussed before. So there I will be covering the proof, and the basic proof has 2 steps. So the first step, we actually show that the binomial theorem holds for small integral values like 2 and 3, and we use the formula basically a plus b whole square and a plus b whole cube. And we put the values of these NCR values, because when we have n equal to 2, we have the expression 2c1, which is equal to 2. Then when we use n equal to 3, we get the value 3c1 and 3c2, both of which are 3. So we get the expansions as a plus b whole square equal to a square plus 2b plus b square, and a plus b whole cube equal to a cube plus 3a square b plus 3ab square plus b cube. That's the first step. In the second step, we use the principle of mathematical induction for higher values of n. That's the basic proof of binomial theorem, which I will be covering in my future videos. So the next topic that we'll be covering or discovering is the Pascal's triangle. This Pascal's triangle was discovered or illustrated by a person called Blaise Pascal. He was a French mathematician, physicist, inventor, writer, and Catholic theologian. So the Pascal's triangle is a table showing the pattern of coefficients in the binomial expansions for non-negative integral index. Before we go to the nitty-gritties of Pascal's triangle, let's do a simple exercise. So you see, I have certain binomial expressions written on this side, and I have written the expansions, the binomial expansions of these expressions on the right-hand side. So a plus x whole to the power 0 is 1, because anything raised to the power 0 is 1. A plus x whole to the power 1 is the number itself. Anything raised to the power number itself is that number. So we have a plus x whole to the power 1 is a plus x. A plus x whole square, using the formula a square plus 2ab plus b square, is a square plus 2ax plus x square. Then we have a plus x whole cube. So we have the formula for this a plus b whole cube as well. We get it as a cube plus 3a square x plus 3ax square plus x cube. If we use the binomial expression and we replace the expressions or the values of NCR in each expansion, we get a plus x whole to the power 4 as a to the power 4 plus 4 a cube x plus 6a square x square plus 4ax cube plus x to the power 4. If you want, you can of course check it. If you do not find it easy to do, I will do it in a future video. Moving on, we have a plus x whole to the power 5 as a to the power 5 plus 5a to the power 4x plus 10a cube x square plus 10a square x cube plus 5ax to the power 4 plus x to the power 5. Similarly, finally, we have, of course, this is not the final, we can have more, but I just took it till a plus x whole to the power x being a to the power 6 plus 6a to the power 5x plus 15a to the power 4x square plus 20a cube x cube plus 15a square x to the power 4 plus 6a x to the power 5 plus x to the power 6. Now, why did I work so much? Let's find out some pattern in this triangle. You see, we have got a beautiful triangle over here. So you see, we have 1 over here. What do you think the coefficient of a and x are in this part? You see, coefficient of a is 1 over here, and the coefficient of x is 1 over here as well. Again, if you consider the coefficient of a square over here, that's actually 1. Coefficient of ax here is 2. Coefficient of x square here is 1. Similarly, we have coefficient of a cube to be 1 over here. Coefficients are 3 over here. And again, we have the coefficient 1 over here. Now, why am I finding out the coefficients, you may ask? This coefficient of ax that we have, 2, you can get it by adding 1 and 1 over here. So this 2 can be derived from adding the two coefficients on its two heads, let's say. Again, this coefficient 3 on the fourth line of this the fourth line of this triangle, this can be derived by adding 1 and 2. So again, 1 and 2 are its two heads. Similarly, this 3 can again be derived by adding 2 and 1, which are located on its two heads. So what I'm finding out is, all the time these numbers that are on the margin, all of these numbers, they have the coefficients as 1. A cube, x cube, a to the power 4, x to the power 4. All of these terms that are on the margin, the outermost or the most extreme terms, they always have coefficients to be 1. The numbers in the middle, those which are not there in the extreme portions, the numbers that cover the inside part of the triangle, each of them, these coefficients can be derived by adding 2 of the numbers on its head. So again, when I expand a plus x to the power 4, I get this expression. This 4 can be achieved by adding 1 and 3 on its two heads. This 6 can be attained by adding 3 and 3 on its two heads. So you see, there's a beautiful pattern over here. This pattern is called the Pascal's triangle. Now, as you can see, this Pascal's triangle has two properties. So the first property is, as I said before, the coefficient of the first and the last term in binomial expansions are always 1. And the second property is, for each of these middle terms, you can get the coefficients by adding the two numbers on its two heads. This Pascal's triangle is essentially a never-ending equilateral triangle of numbers that follow a rule of adding the two numbers above to get the number below. So 2 of the sides are all 1s, and because the triangle is infinite, because we can move on to a plus x whole to the power 7, a plus x whole to the power 8, this triangle, there's no bottom side. Moreover, as I mentioned before, this is an equilateral triangle. So if we count the numbers 1, 2, 3, 4, 5, 6, 7, again we have obviously 1, 2, 3, 4, 5, 6, 7 terms, and 1, 2, 3, 4, 5, 6, 7 terms on its bottom side as well. If we move on to the next line, we'll again find that there are 8 terms on this side, 8 terms on this side, and the expansion of a plus x whole to the power 7 will naturally have 7 numbers. 7 terms to be exact. So the next thing that we'll be covering is important binomial expansions. So this binomial expansion is essentially the normal binomial expansion. Instead of a, we replace a with 1. So we already had a plus x whole to the power n expression written above. What we essentially do is we replace a replace a with 1 on both sides. So we have 1 plus x whole to the power n equals 1 plus nc1x plus nc2x square plus dot 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 dot. The r plus 1th term is ncr x to the power r plus the last term is x to the power n. So initially we had a to the power n, that a to the power n becomes 1 to the power n, which is 1. The next term we had nc1 a to the power n minus 1x. Again, a to the power n minus 1 becomes 1 to the power n minus 1, and 1 to the power anything itself is 1. Similarly, the next term we had nc2 a to the power n minus 2x square, which is again the a to the power n minus 2 part of the second term again becomes 1. Similarly, we get the rest of this expression. The next term, instead of writing plus x, we replace x with minus x. So initially we had a plus x whole to the power n. In place of x, we replace minus x. So we have a plus minus x whole to the power n. That becomes a minus x whole to the power n. And what we initially had is, let's say this was plus, and instead of x, we replace on this side as minus x. So what we had is a to the power n plus nc1 a to the power n minus 1 into minus x. That minus comes out. That gives me the second term of the expansion. The next term, this x was to be replaced by minus x. So what happens is we get the third term as nc2 a to the power n minus 2 minus x whole square. Minus x whole square essentially gives me x square. So the plus term is the third term is preceded by the positive sign. So going on, we have the expressions as follows. And as you can see, the second term is negative. The third term is positive. So whatever term we consider, if that term is, so if we have the second term, that is second 2 is an even number, and when we have an even number, the sign is negative. When we have an odd term, the sign is positive. So this is the r plus 1th term. If the r plus 1th term is even number, then it's preceded by a negative sign. And if the r plus 1th term is odd number, then it is preceded by a positive sign. That is how we get the expansion. Similarly, we get 1 minus x whole to the power n. That is a basic combination of the two previous concepts. Again, we have, as I have mentioned before, tr plus 1 is ncr a to the power n minus r x to the power r for the expansion of a plus x whole to the power n. And we have a minus 1 whole to the power r term for a minus x whole to the power n.